They're called polyextremo tolerant.
Their schools are too cold, or they're too hot, or there's flooding in the streets and they can't get to school.
Extreme heat is the #1 weather-related killer in the US.
These are all really extreme environments.
Are they found in our homes?
Home diagnosis is made possible by support from Brown Newton. Better air, better life. By the Got Mold Test Kit, real science, real simple. By Air Cycler, RetroTech, Rockwool, and Renew Air. By generous support from these underwriters and by viewers like you.
What is an extreme environment, and could we actually live there?
Too late, you already do. Remember, only a few insects can survive in the conditions we think of as comfortable in homes.
So we are extremists, surrounded by a world increasingly prone to extreme weather events.
And building faster and cheaper than ever in areas that haven't already been built on.
Huh. I wonder why no one's ever built a house on a lava flow. Seems so affordable.
It is in a floodplain, but I'm sure it's fine.
It's the shields we build. And the risks we take. It's the disasters that will test us. And what will grow from them. It's real life. And the physics, chemistry, and microbiology of the science of homes.
Hawaii is a unique location for a number of reasons. One, it's a series of beautiful tropical islands, far enough north of the equator that we're not subject to the extreme heat of being on the equator. We're subject to hurricanes. We're a very small target in the middle of the Pacific Ocean, but we have been hit by hurricanes and we will be hit by hurricanes in the future, so we have to design for them. Because of the volcanic activity in the Big Island, and because of the weight of the islands sitting on the oceanic plate, we're also subject to earthquakes. The potential for severe earthquakes in the Big Island of Hawaii is as high as anywhere in California. On the Big Island, we have to design seriously for earthquake design. And the other coastal hazard is tsunami. We're at the middle of the Pacific Ocean, and the ring of fire, the subduction zones around the perimeter of the Pacific Ocean, all can generate massive earthquakes which can produce tsunamis. We're also faced with droughts. Even though we have a fairly consistent trade wind and rainfall history, it means that the vegetation is reliant on that regular feeding of rainfall. So a couple of months of dry time ends up being a drought. Whereas in California or other desert areas, drought would have to extend for a few years before it becomes a serious issue. Droughts can exist even in a place that's known for being wet. The rainfall intensity can be very high, and so we've had flooding in rivers that damages homes, damages bridges, and it has cost a few lives in the past when people don't evacuate. Hawaii has volcanoes. That's what built the islands, and so the Big Island of Hawaii is still an active volcanic zone. We regularly have lava flows that produce new lava, and we had one just a few years ago that ran just south of Hilo, the main city on the Big Island, and destroyed a number of houses in a community on the south side of the island. And those properties now are covered with fresh lava. But people still own the property. And so there are those who are wanting to go back and rebuild on the same place that was just wiped out by a lava flow. There are others who would rather get reimbursed for their property. People knew that that was lava terrain. It's listed as the highest risk area for lava flows. Nevertheless, they bought those properties because they were cheap, and they built houses on them. And then the lava came, as predicted, and took away the house. Now they feel like they should be reimbursed. And we have the same thing with coastal. Now people living on the coast, they paid $10 million for a house on the beach, knowing about climate change. Nobody can say they don't know. And now that house is falling into the ocean and they expect somebody to pay for it. If we've made people aware of the hazard, then they should be responsible not to put themselves in the path that has it. But yes, building on lava is always risky because it's proof that that has been a recent flow, and we shouldn't be building there. Nevertheless, one of the airports in Kona, the Kona side of the Big Island, is built right on a lava field from the early 1900s. And that side of the island could see another lava flow. And so that airport could be in jeopardy, as well as the whole town of Kailua Kona. There's no research on trying to protect homes from lava, particularly when we build our homes out of timber. They burn almost before the lava gets there because of the intense heat. But even if you build out of concrete or steel materials, there's no real point. It'll overwhelm it. It won't be any use after the event. Some people have discussed the issue of diverting the lava flow before it gets to occupied or built up areas by building rubble mounds and trying to get it to flow in a particular direction. Others have thought about what if we cool down the leading edge, bring all the fire trucks and we spray water, or we bring airplanes, right? So that we can freeze that section and get it to move another way. And some of those have been tried unsuccessfully. And the problem is that we then don't know what harm we're doing. We might be saving one community but directing it towards another. And so the current approach when you have a lava flow is to let nature take its course and just get out of the way. So yes, it's an interesting place to live.
Extreme heat is the #1 weather-related killer in the US, more so than hurricanes or earthquakes or floods. We've done some research that shows that across the US, especially across the Sun Belt states, you have about 50 million people living in cities where the housing stock is such that if you had a major power outage within 4 to 8 hours, you would be in dangerous conditions. It's not a matter of if we have a major power outage in cities like Phoenix, it's really a matter of when. A major power outage I define as one where you lose power for at least 10 hours and affect at least 100,000 customers. Over about a 15-year period, there were 525 major power outages in the US. When you combined extreme heat with lack of power or lack of functioning air conditioning, that's when people die indoors.
British Columbia traditionally has had quite a temperate climate, especially in our coastal areas where most people live. So air conditioning is uncommon here. At the end of June 2021, we had one of the most extreme hot weather events ever recorded on the planet. Hundreds of people died during this event over the course of the 1 week. Now, people didn't die because it was hot outside. They died because it was hot inside. Almost all of these deaths occurred in private residences, and almost none of those private residences had any evidence of working air conditioning.
In Phoenix, virtually every home, every apartment has an air conditioner of some sort. Whether they work well, whether they're maintained, whether they're actually blowing cold air is another story. And so what we found is that those living in poverty, the elderly in particular, are very much at risk of extreme heat adversely affecting their health. The homeless population is also very much at risk. And there was a recent study from a colleague of mine that suggested that if you lived in a mobile home in Phoenix, you were about 5 to 8 times more likely to die of extreme heat than if you lived in any other type of housing in Phoenix.
As the planet heats up, what is going to happen to children? And in particular, what is going to happen to children in their schooling? Many of the schools in the United States are simply not prepared for the longer, hotter days that we are going to face. And so some scientists project that thousands, tens of thousands, maybe even millions of school children are going to have to miss school every year because the school buildings are too hot. Conversely, we know that many schools in our nation are also too cold. And so in Baltimore, for example, every year school children there already miss school because their schools are too cold or they're too hot or there's flooding in the streets and they can't get to school. And that's just one city in our nation. Sometimes I'm asked this question, is the solution just to put air conditioning in all of the schools? But we know that air conditioning also comes with an environmental price. So you solve one problem, but then you maybe create another one. What can we do about that? Both the technical fix, short term, but then there's a longer term social fix that we need to think about. And I think it's bringing those two things together is where the breakthroughs are going to occur.
We were funded by the US EPA to look at the combination of extreme heat and poor air quality in a changing climate and the impacts especially on the most vulnerable population. So we chose to look at elderly living in these private assisted living facilities. So these are typically just large homes scattered throughout a city. And so we were looking at this population in Houston, Texas, when Hurricane Harvey came through. So what happened during Harvey was that there were a number of buildings and homes that got flooded out. You ended up having a lot of people come together in smaller spaces and not be able to go outside as much. And so in a number of the homes that we were monitoring, we saw these large spikes in CO2. There has been an established link between cognition and CO2 levels. But when you combine high levels of CO2 and potentially degraded cognitive abilities in a population that's already seeing that cognitive decline, so a lot of these are Alzheimer's patients. If you look at CO2 readings, say in the common areas where most of the residents would spend a large portion of the day in front of a television and in conversation, and we would easily see CO2 levels that would spike up to 1,500 parts per million and higher. And then, of course, when the hurricane hit and we had even more people confined into smaller spaces, we saw spikes to 2,000 or even 3,000 parts per million. And this, to me, was a very interesting outcome because it started us thinking about a potential adverse outcome that's oftentimes not really thought about, which is for that elderly population in particular, are we making the course of their disease worse by having them in high CO2 environments? And at the moment, we don't have an answer to that question because there has not been a dedicated study looking at the elderly and elevated CO2. Most of my work in Los Angeles has focused on the urban heat island effect and potential to mitigate it. In fact, that was the topic of my dissertation defense. Back when I was in grad school, I was looking at the city of Los Angeles, by how much can we cool the city if we either plant a lot of trees or increase the reflectance of a lot of surfaces. And it's really interesting. I kind of come full circle where I'm still looking at Los Angeles, but through a slightly different lens. So like one thing that we do now a lot more than we ever used to is we recognize that the problem is not uniformly spread through any city, and it's not uniformly affecting all subsets of the population. So I am very much focused these days on the concept of targeted heat mitigation. Find out where you have this overlap of extreme heat, extreme vulnerability, and extreme risk. Look at that overlap space. It's only a handful of neighborhoods. You could put the same amount of resources into cooling those neighborhoods that you might say for the entire city and have a much larger benefit to the population in terms of reduced adverse health outcomes and reduced deaths.
One of the first thoughts after the discovery of extremophiles was, are they found in our homes?
So your oven's an extreme environment, your freezer is an extreme environment, your hot water heater, your salt shaker, the little soap dish in your dishwasher, which is typically very alkaline and it's hot and then cold and wet and then dry. These are all really extreme environments that if we scaled them up, we couldn't live in them. But there are microbes from all around Earth that think these are the best places ever.
So looking inside the dishwasher, why would scientists be interested in just the dish soap container?
So you will find microbes everywhere in a dishwasher, but what's really interesting is what's left after you run a dishwasher hundreds of times. What's left over are the things that can survive those extreme conditions.
They're called polyextremo tolerant. They can tolerate all the extremes in both very cold or very warm, or very low pH or very high pH. And what they can't really tolerate is dry things. They have to have it good on at least one parameter in order to tolerate the others.
What are we learning from the microbes that can last 100 cycles in a dishwasher?
First of all, we don't know about all the microbes on the planet. There are, billions of different kinds of microbes. Humans have only studied in detail a small number of those. And for people studying things that grow at high temperatures, for example, they usually have to go to a place like the bottom of the ocean, remote environments, difficult to go collect routinely. But those kinds of microbes show up right in front of us. It's a very convenient way to study them.
Fascinating. This is an extremely hot environment. There is an extremely cold environment right behind you. Can we talk about the refrigerator and freezer?
Yeah, so a lot of people think that if we put something in a cold environment like the fridge in particular, that sort of shuts off microbial growth, but it doesn't actually stop microbial growth. It slows it down. And so if you leave something in the fridge for a long period of time, especially if it had gotten contamination from the air or from some other place, some microbes can just keep growing, and some of them actually prefer to grow in those cold conditions. If you open up someone's fridge and you look inside of it, you will see, mold frequently growing in spots, especially the wet spots. So microbes actually, some of them can thrive below freezing point of normal water if there's salt or something else in that water.
Our refrigerators and our freezers, they are sealed with silicone and rubber sealant. And there we have fungi growing. We have Cladosporium, we have Exophila, we have Candida, and they actually can get some kind of nourishment, we think, out of the silicone material.
Another thing that people frequently have is a water dispenser. But microbes like water, so if you leave it sitting for a long period of time, things can start to grow in it. So you have to be sort of careful with that.
So Jonathan, here we are in the bathroom, which is definitely one of the best rooms, and yet it's also one that gives me extreme anxiety when I think about microbes. Is this an extreme environment for microbes?
Yeah, I mean, in most senses, probably not, but it is the place that most people worry about microbes in their homes. But it's also true that there are not just bad microbes in this environment. Even in the bathroom, there are also beneficial microbes. And if we try to kill them all, that actually creates a bad system. So in general, it's useful to clean things, it's useful to wash your hands, but it's excessive to put like antibiotics and antimicrobials into these environments. That leads to organisms becoming resistant to those antimicrobials, and those can then spread into people and create infections.
Bathrooms are also very wet. There is 2, 3, 4 fungi that seem to thrive very well in our bathrooms. And they're more yeast-like fungi. A yeast is basically a one-celled fungus. One is Cladosporium, and it is very fond of growing between the tiles in the cement grout. And the only way to keep it down is to wipe the bathroom every time you've been showering.
Wildfires are becoming more and more prevalent, and the microbial life that enjoys a fireplace possibly would enjoy an entire neighborhood that has been burned down. Am I correct?
Yeah, I mean, so the microbes that colonize wood after it burns, for example, are going to be the same kinds of microbes that you would see, on the wood in a fireplace versus after a fire has happened. And for the big wildfires, it's not just what happens after the wildfire, it's what happens during the wildfire. So there are microbes on the leaves of plants, there are microbes in the wood, there are microbes in the dirt. Those get mixed up during the wildfire and dispersed to other places. That could be useful in some sense because it's moving the microbes around. It could also be dangerous because we inhale the particulates that are getting spread by the wildfires, and there are going to be microbes on that. And then what happens afterwards, the system has been somewhat decimated, but there are microbes that survived that, and now they have sort of a non-competitive environment to grow in, and so all sorts of changes happen after the wildfire.
So Jonathan, the garage is a perfect place to put your water heater, I like my laundry inside the house, but this is all still very much a part of the home.
Yeah, and the water heaters are one of the most interesting microbial environments in any home.
Some of the species in hot water heaters also live in hot springs. The enzyme in the bacteria that is found in hot water heaters is the same enzyme that makes most modern genetic analysis possible, because it works at high temperatures, and so we can use it in the lab at high temperatures, and we can copy DNA really, really quickly using it.
Microbes disperse through water and through the air and through dust and dirt and on animals. So there are some that have been shown to get distributed by migratory birds. And most of the time, when they get into a human-built environment, they don't thrive. But some of them that get into the hot water heater, then they thrive. And it turns out that this is a great way to study those organisms because, again, it's really hard to go collect from some of those environments. And yet we have hot water heaters in millions of homes, and they're each slightly different than the other one. They have slightly different chemistry of the water, they have slightly different shapes, they have slightly different mixing, they run at different temperatures, and each of those create a slightly different environment where you might find a different kind of extremophile.
One interesting thing about microbes is that a lot of environments that we thought were potentially sterile turned out to not be sterile. And that's true of, for instance, parts of the human body that we thought were sterile previously, and it turns out have their own unique microbial communities. We have been absolutely thrilled to work with NASA to help understand the microbes on the International Space Station and what's going on there. Previously, the space station Mir did not have great control over relative humidity on board. So at the time of its decommissioning, it had fairly extensive fungal growth that was affecting things like wiring and window seals, which are obviously critically important if you're in space.
When people study the International Space Station, which is full of microbes, they're worried about the species that can do well in this sort of mix of conditions and their potential to colonize the astronauts. The Russian space station, the Mir, is a good example of this. So it was covered in microbes. And in fact, when it would get humid in the Mir, there was a point when the windows actually were covered over with fungi that they couldn't look out the windows.
We learned a lot of really important lessons from that. And when we built the International Space Station, we have much better control over the relative humidity and the moisture. If you think about the space station, it's this enclosed environment with zero ventilation, and we have people inside, and people breathe out moisture. We sweat, we sneeze, and contribute this moisture to the indoor environment. And so it's really important that that's very carefully controlled in this extremely specialized environment to make sure that you don't have unwanted microbial growth in the space station. So one thing in the International Space Station is that the dust is floating around regardless of particle size. Down here on Earth, the smaller particles, around 1 micron in size especially, tend to stay airborne for extended periods of time. On the International Space Station, you're going to have dust remaining airborne regardless of size until it gets captured on the cleaning system on the air vents that they have up there. Air also doesn't move on the space station naturally like it does on Earth due to convection, where hot air rises. Because there's no gravity on the space station, you're not going to have that same effect with hot air rising. So you have to have fans that mix the air on the space station and move through the ventilation system with that air movement.
I live in Boulder, Colorado. And Boulder, Colorado is this exquisite place. It's this beautiful place. It's also, like all other places, getting hotter. It's a place that is high, but it's also dry. It's also perhaps the most flood-prone community in all of Colorado. And so I am now raising this little boy in this context where we have flood risk, we have fire risk, we have increasingly hot days. And so there are all these extremes that are unfolding all around us. And so every single day I think about that. I think about, what is this going to mean for his future and his ability to get an education and to learn as the climate's changing all around him? And what does this mean right here at the local level But then these are really global problems. And so this is, I think, one of the great challenges of scientists and engineers who are working in this space is how do we develop really locally specific solutions to the problems we're facing that make sense for the communities where we live, but then also how do we never lose sight of the scale and the scope of these problems, because there's such a deep interconnection, but it's also what makes doing anything about this really hard.
And the scale and scope of these extreme hazards we're facing are also changing as we go.
We've only touched on some of the glaring societal issues that make disasters so different for different people. So we've actually set aside the final episode of this season to focus entirely on that.
But up next, we'll go tiny again to tour the incredibly colorful science of mold in homes.
For practical solutions and extended interviews, visit homediagnosis.tv. Bye for now.
Home Diagnosis is made possible by support from Brown Newton, Better Air, Better Life. By the Got Mold Test Kit, Real Science, Real Simple. By Air Cycler, RetroTech, Rockwool, and Renew Air. By generous support from these underwriters and by viewers like you.